Hello everyone, my name is Mirtriello. I'm part of this AI course, and this is the project for the first to complete the module. And it's a training a model. I use Google Cloud to do that, and basically what I did is to upload all the information provided on the course, and also I enable Vertex AI with all the APIs that are required and the subscription. So first of all, I uploaded the CSV file provided with all the information and all the values, and created two models. These models, I'm just going to give you an example of how I did it. It's part of the AutoML pipelines. And what it asks you is just to uh, enter where you want to store the results. The objective type is the type of a model that you want. In this case, it's going to be a regression. And the most important thing, what value is going to be your base. I've selected PE for the first one and going forward with the features with the other ones. The second model that I use, I did exactly the same, but I removed RH just to have a comparison with the values that we are using. Having them train, it lasts for a couple of hours each, and it gave me a good results. Initially, it wasn't easy to set it up, but once it's complete, it runs smooth. So the first one, and it's just to give you a little bit of background. A PE, it's a part of the information that we got. It ranged between 420 to 496 megawatts, and that's what I use all these different features. That is the ambient temperature, the pressure, humidity, and the exhaust vacuum. So let's take a look to what I did with on the first one. That is with all the information, and we have these values. I'm just going to click here to show you what we got. First, our MAE, or mean absolute error, that is 2.4 megawatts. This means that on average the model predictions differ from the actual observed power output by 2.5. So it's not too much. And that 2.5 is megawatts. So given that scale on the power plant's operation, where outputs are generally in the range of what I mentioned, between 420 and 496 megawatts, these 2.5 megawatts of error is less than 1%. So for a typical deviation, it's not a big problem, and this level of accuracy is quite acceptable for the operation and forecasting of this power plant. The next one that we have on the right is the MAPE, or the mean absolute percentage error, and it's just 0.5%. So it's telling us that on average our model predictions are approximately half a percent of the true values. So as our professor said, a value below 1% is excellent, especially for these industrial applications, indicating that our model provides a high or a good precision in our predictions, uh, thinking about what we are doing on the plant. That low percentage on our error says that our model is accurate and can be used for short-term and long-term forecasting without having any significant risk on large deviation. The other one that we have is a RMSE, or the root mean square error, that it's a 3.2 megawatts. That's a kind of similar to MAE, but it penalizes larger errors more heavily because it squares the difference. So what we have here is that this low value of our MSE, it's telling you that we can trust on it. It assures us that the occasional prediction errors, and when they occur, it won't have a big impact, or won't affect our operational decisions. The other one is the R square value, that it's our coefficient of determination, that it's only 0.9%, 0.9, sorry, I was saying that it was 0.9%. This module, it's telling us that 96.3% of the information that we have here demonstrate the accuracy and consistency of our model. So 0.9 in R square is an excellent value for regression. The second model that I run, and I'm just going to click here again just to show you all the graphs and what we have here, how this looks on Vertex AI. It's pretty simple. It gives you the chance to compare multiple models. I'm going to show you after explaining the second model, and it's exactly the same situation. I just selected the features, all the inputs, and that's where we have a similar values. MAE, the first one, that's again our mean absolute error is just 2.5, and in average that's a good percentage. So we don't see any problem here. Being just below the 1%, that's a good number for us. The next one, it's that 0.5 on MAPE. That essentially, that low percentage error means that even under varying environmental conditions, our model maintains a high level of precision. So we're good. Having 0.5, it's good for us. The 3.2 value, that it's in this case megawatts, it's telling us the average magnitude or size of our errors. But here's the thing, it penalizes larger errors. Always our MSE, it's going to penalize errors more drastically because we are doing the square factor, that it's squaring all the differences. This number, it's good. Again, it's telling us that our model is consistent in predictions and everything. So if you've seen, we have all this information. It looks similar. Let's compare what we have here. I'm just going to select both. And what we have here, finally, it's telling me that both models achieve a good performance predicting the power plant output. The model 1, it's the blue one, it's predicting that it has better results with lower MAE, and but both models share the same low RMSE. So we are good. Data is consistent. We don't have any larger difference between adding inputs or removing inputs in this case. So we can use this model and this data to predict our power plant outputs. Thanks so much.